Hey freeCodeCamp, welcome to another The Daily Programmer web series video. The problem today we're going to talk about is called Color Maze, which is number 325 on the Daily Programmer subreddit page. Alright, so here is the problem statement posted on the subreddit. I'm not going to read through the whole description, but I'll go ahead and give you an overview. Basically, he attaches an image, or two images. The first image is your 2D array, which has your color matrix. And then your goal is to find a path from the bottom row to the top row, which matches the sequence. So in this case, he gives us a sequence of orange-green. So our sequence is orange-green. So at the bottom row, if you can find an orange node, and then traverse to a green node, and then again traverse to an orange to a green, orange, green, orange, we've found a path which matches that sequence inside the provided 2D array. So that's the goal. Again, given a grid, find the path from bottom to top, which has the exact sequence we're looking for. And then inside here, there's a couple of criteria. It says you can move horizontally and vertically, but you cannot move diagonally. And you're also allowed to move to, it is also allowed to move on the same node more than once. So if for some reason you have to like go up the grid and then cut through somewhere you've already been, that's allowed. And then for the input, the first line is a color sequence. So again, O space G would be our color sequence, and then followed by that is our grid that we're trying to solve. And then he says that you can output the path that solves the matrix, or you can just go ahead and print out the matrix with that path printed out inside of it with empty strings and all the other locations. So for our case, let's just go ahead and try to solve it to print out this actual grid so we can visualize it. And then we're not going to worry about trying to parse this input. We're just going to write a function which takes in a sequence array and then also takes in a 2D array of our grid. Yeah, so that's basically the problem. Let's go ahead and work it out on the whiteboard with a really simple solution. All right, so let's start off with a really simple example here. So again, we have the sequence of O and G, and we have this grid, it's just, which is 3 by 2, so 4 rows by 3 columns. And remember, the goal is to start at this bottom row and find a path, which happens to be this path that I'm motioning out with my hand from the bottom left corner to the top right corner, where you can only move vertically and horizontally to match the next color in the sequence. So again, let's work this out by hand. So the algorithm starting off is you pick the first index of your sequence. So for this algorithm, we're going to do something like a breadth first search, where we pick the first index of our sequence. So in this case, we have the color O. And we need to find the bottom elements, so all the elements on the bottom row, which match the current sequence that we're at. So in this case, we only have this bottom left corner, which is equal to O. So one more time, we initialize and start with the first element of our sequence. We go to the bottom row and find all the elements that match that sequence. And then we can go ahead and push that location, which is 3, 0, to some type of list or queue. So I'll go ahead and put a 3, 0 here for our cells or paths. And that's iteration 1. So iteration 2, we go ahead and increment the color that we're looking at in the sequence. We check the vertical and horizontal locations that we can move to from our current location. So a current location would be, we pop off the first element of our current cells list. So in this case, we have 3, 0. And then at 3, 0, we just check, can we move to 2, 0? Can we move to 3, 1? Do they match the color that we're currently at? In this case, the only match that we find is 2, 0, so we can go ahead and push 2, 0 to our array, and then go ahead and move to that location on our next iteration. So iteration 3, we increment our sequence, so we go back to the O here. We pop off the first element of this list, so 2, 0, which puts us right here. We then add on every vertical and horizontal location that we can move to, which matches this color of the sequence O. And then one caveat is we can kind of ignore the one that we've already been to. Since that last previous location was this O, there's really no reason to go back and check. So in this case, the only location that's a kind of a new location is 2, 1. So we can push 2, 1 here. And then go ahead and move on to iteration number 4. So again, iteration 4, we pop off the first element. So we're put at 2, 1. We increment our sequence. And then using the same logic, we can just add on every location which is vertically or horizontally adjacent to this location, which matches the sequence of color G. In that case, it would only be 1, 1. So we can just go ahead and add a 1, 1 here. And then repeat our steps. So iteration 5, we're pointing at O now. We pop off 1, 1, which puts us at 1, 1. And then we check every location where the previous isn't equal to. So in this case, we can check this, that, and there. And this happens to match O, so we can go ahead and push 1, 2. Iteration 6, we remove 1, 2, which puts us at 1, 2. Increment the sequence. And then we check, and it happens to be that 0, 2 is the only location we can go to. And then for our final iteration, 7, we remove the slot. And throughout all these iterations, you basically check if we're ever at row 0, we've kind of solved this problem. So in this case, we're popping off the first element. We get 0, 2. We check, okay, 0 is equal to row 0. So therefore, we found a solution. So this algorithm kind of shows you that, yes, there is a solution where you can get from the bottom row to the top row. But then you might say, okay, well, how do you keep track of the path that we took to get from there to there? So basically, all you can do is just, instead of having this array, you can make this an object, which has the I and J location you're about to move to, and it also has the previous location as an attribute, which points to another object. So if you imagine, we could have each one of these is kind of like a node, which points to the previous. So in this case, this one, its previous pointed to that. This one's previous pointed to that. This one's previous points to that. Previous points to that, and points to that. So ultimately, if you, instead of using arrays to build up your paths, what you can do is use objects that point to other objects to kind of traverse backwards to the path that you found. So in this case, we'd have 0, 2 points to 1, 2 points to 1, 1, which points to 2, 1, which points to 2, 0, which points to 3, 0, and then we can just print that out here. And that is basically the algorithm for how do you use breadth first search to traverse this grid to find a path which matches the sequence. And this will make a little bit more sense as we implement it in JavaScript, because like the whole keeping track of the path thing might be a little bit confusing, but I think it'll make more sense when we see it in code. And then also there's little caveats where to, like, if let's say there's multiple start locations, this algorithm will still work. It'll just take longer because we have to pop off extra locations and move each one individually. And I'm not going to work through a larger case because obviously this took a lot of time, but try it for yourself. Hopefully it makes sense. Let's go ahead and implement this in JavaScript. All right, so just a heads up, this implementation is probably going to be a lot harder than any of the other ones that we saw in the previous daily programmer challenges. But hopefully it can make sense after we go through all of it. But basically, again, let's just get started. We have a sequence which has an array of the sequence we need to iterate through, and then we also have a maze constant, which is the actual 2D grid that we need to find a solution throughout. And then down here I have line 12, which is just calling a solve method, passing the sequence in the maze, and then we're printing out the path. So let's go ahead and create a solve function here, which takes a sequence in a maze. And then inside this function, what I'm first going to do is just declare a couple of helper variables. So I'm going to say const rows is equal to maze.length. So that's just a constant which tells us the number of rows we have in the array. And then I'll say const calls is equal to maze of 0 dot length. And that'll tell us how many columns are in the matrix. And those are, again, just kind of helper functions that we'll use, or helper variables we can use. Okay, so another thing I'm going to do is go ahead and declare a generator. So if you don't know anything about ES6 generators, you might want to read up on that. But basically, we want a generator, so every time we call it, it'll give us the color. And then once we reach the end of the sequence array, we just go back to the beginning, and it just keeps on returning us the color sequence. So I'll go ahead and say const colors is equal to, and I'll say this is going to be a self-executing function, which takes a parameter of I, which is equal to 0 by default. And again, if you don't know what a self-executing function is basically you create a function and then call it right then and there so that it returns something. So in this case, we want to create a self-executing function which returns a yield, or which does a yield, and that's how you pretty much do it using generators in ES6. Alright, so again, this is a generator function which is going to keep on looping over each sequence in the list, and then once I goes out of bounds, we go ahead and modify the length so it goes back to 0. So this will give us OG, 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 OG if you keep on calling it again. Alright, so we have a rows constant, we have a columns constant, we have a color generator constant, which we can use to kind of implement our algorithm. So the first thing I'm going to do is, again, the algorithm says we start at the bottom row, right? So we need to grab every cell that's in the bottom row. So I'll go ahead and say let paths equal to paths, or maze of the last row. So maze of rows minus 1 will give us that very last row. And I'm going to go ahead and filter out, or sorry, I'm going to go ahead and map that to an object. So in this case, every index we want to keep track of, so we can say rows of -1, j of j, and then previous, like we mentioned in the whiteboard, is just pointing to another object, which is how we traverse back. So in this case, let me just reiterate, we grab the last row. For each element in that row, we're going to return an array which has an I, a j, and a previous attribute inside an object. So here, if I were to just say, let's just print out paths so we can see what's going on here. We see that paths is an array of 5 elements where we have I is equal to 4, which is the last row, and then we have j of 0, 1, 2, 3, and 4. Right? So that's kind of what we're going to start off with, and then we can go ahead and filter it out to only match the colors of our current sequence later on. Okay, so now we have our initial paths. We can go ahead and loop through our colors. So this is how you can loop through an iterator, or a generator in ES6 if you want to. Basically just a normal for of loop. So if I were to print out color here, it should print out O. And if I were to print out in the next iteration, it should print out G. And if I didn't have this break here, it would just infinitely loop forever. So I'm going to keep the break in there for now. Starting off, we want to, like we said on the whiteboard, we want to grab and filter out anything that is out of bounds. So first of all, we can say paths equal paths, and we're going to use some like functional programming to just keep on modifying the paths array. So we can first filter out every path that is out of bounds, right? So we can say if path of I is less than rows, path of I is greater than or equal 0, if path of j is less than columns, and path of j greater than or equal 0. So basically this will give us, or this will filter to only give us the cells which are valid or inside of the grid, because later on we're going to push values that might be potentially outside. Kind of a little bit different from the whiteboard algorithm, but I'm just going to do a little bit different on this implementation. The next step is we need to filter out every path that doesn't match the current color that we're at. So if I were to just do filter paths of base of I, path of j is equal to color. Again, this will give us only the paths which match the current color that we're at. And so in this case, color O, if we were to print out what paths is here, it should make sense that it only gives us the fourth row, the last row, and then that column 1, right? Because if you look over here, that's the only thing that matches O. So again, we take every element in the bottom row, we filter anything that's out of bounds, and we also filter to only match the color that we're at, which will give us this one location of O. And then finally what we want to do is for each, remember we pop off the first element and we add it to the end, and we keep doing that. So what we can do is just do a reduce function where we have we're going to build up a new array and just keep on returning a new array with all the elements pushed to the end. So if I were to say reduce, where we keep track of the accumulator, go ahead and pass an empty array to reduce. And what we want to do here is just go ahead and say accumulator concatenated with, and then I'm going to do the 4 locations, so horizontal and vertical. So I can say di of 1, dj of 0, and then di of -1. So this should be the direction going up, direction going down. Actually, I think that's swapped. Direction going down, direction going up, direction going to the left, direction going to the right. So for each of those directions, we are going to simply map those to an object, and that object is just going to be our current path location added to the direction. So if I do I is equal to path of I plus dir of d of I, and then same thing with the j, we can say j is equal to path of j added on to dir of j. All right, so again, taking a step back, we started off with that one element, right? And then we're going to reduce over that array, which is going to be one element. And for each element, what we do is we add every potential location you can go to and put that to the end of the list. So in this case, we're going to add the element that's above, which is what we're doing with this whole make an array and then map it. And then for each mapping callback function, we just take the current location of the path and add it to the direction. So you can see here we have, after this runs once, we have a new array. So path is equal to array of 4, where each location is the top, bottom, left, and right location. And you can see some of these are out of bounds, which is why we have this filter up here, so that we filter on the ones that are in bounds. And some of these locations may point to places in the grid which are not equal to the current color sequence. So that's why we have the filter here. And then that keeps on happening where we just take a spot, add the 4 to the end, take a spot, add the 4 to the end, and we just keep on looping that until we find our very in case, which again, if we just say, if we reach the top row, we can just go ahead and return our in. So I'll say const first row paths is equal to paths.filter, and we want the paths which match the very top row. So I'll say filter out the ones and give me the ones that are at the top row. And then I can say if first row paths.length, so that means we found one, we can just go ahead and return first row paths, like so. So go ahead and remove the break statement. And down here, this is working as intended. So it's printing out the path here, right? So we have the first location is 0, 3. which is 0, 1, 2, 3, which is here. Second location is 1 and 3, which is here. The second location for that is 2 and 3, which is here. And then previous, again, is going to be an empty object. So I'll go ahead and stringify this so we can actually visualize what's going on. Alright, so our algorithm, or our function right now, is currently returning this huge nested list where every previous is the previous node. So again, I'll just go ahead and walk you through this. We start off with 0, 3, which is here, and then we go to 1, 3, and then we go to 2, 3, and then we go to 2, 2, and then we go to 3, 1, and then we go to 4, 1, and then we are done. So again, that's pretty cool, but we want to actually visualize it inside the matrix here. So let's write a new function which takes a maze, takes a path, and what it does is it returns a new array which has only that path highlighted. So I can say print path in maze is our function. And that's going to take a maze, and that's going to take a path, or paths. And what we could do is just go ahead and create a new 2x2 grid. So I'll just say blank is equal to arrays of maze.length, fill it with underscores, and then map that to another array of maze.length, fill that with underscores. This needs to be maze 0. So this will give us an m by m matrix here. And then what we want to do is loop through all of our nodes, or go through our paths. So I need to write some type of helper recursion function, which is going to just overwrite the locations of all the paths inside the blank array with the original color string of our matrix that we pass in. Okay, so one more time, what this function is doing is we're recursively diving down all the paths and then replacing the values or indices inside of our blank array with the corresponding values of our original maze that we pass in. So down here I can say const m is equal to print path in maze. I could pass it maze, I could pass a path, and then I could say m to see what that gives us. And we see down here it prints out the maze with the path highlighted. Cool, so I hope this solution wasn't too confusing. Now that I'm explaining it, I think this was pretty confusing. But again, this was a harder algorithm to implement. And I also used kind of like a functional approach to using like as many filters, maps, redos as I could. Again, if you have a different solution, or you think you have a better solution that's more straightforward, feel free to paste it in the comments. And also, if you like this video, be sure to subscribe to freeCodeCamp and like the video below. And I look forward to more videos in the future. All right, thanks for watching.